All right, we're going. So the last example in the notes is example 15, and this is like the last question, I guess, on the worksheet. We're going to decompose now the following algebraic expressions into a composition of a trig function with an inverse trig function. So we're starting with an algebraic expression, and just like in the warm-up, we want to decompose it into a trig of an inverse trig of something. Or it could also be a trig function. What's another way to write an inverse trig? Arc trig, yeah, of something. And you're going to see in this case, answers may vary. There's more than one way to decompose it. All right, first things first. All the information that you're going to need to decompose this is contained within the radicand. All the information that you need to decompose this is contained within the radicand. The first thing you want to do is look at the two terms under the radicand. They're both positive, right? Let's come back up here to 14a. Recall that that was, when we were going forward, another instance where we had two positive terms under the radical. When that happens, it is because you have the two short sides given, okay? And then the radical itself ends up being the hypotenuse. And the reason they're both added is because of the Pythagorean theorem, right? Short side squared plus short side squared equals the hypotenuse, okay? So whenever you have the radicand, here's what you're going to do. It's really the square root of a squared plus b squared. And your short sides are going to equal a and b. And what's nice is you have the choice. You can let a equal one of the short sides be x or one of the short sides equal y. It doesn't really matter. Okay? Then if a and b are the short sides, then the hypotenuse, which yesterday we agreed would be r, right? That's going to be the what? Not the denominator. Let's come back up here. The hypotenuse ended up being not the radicand, but the entire radical. Yeah. Then the radical itself is going to be your hypotenuse. Okay, so that's what we did going forward first. You have to make connections. You have to see patterns. All right, so let's see what we could do with that then. Under the radical, I have 1 squared plus x squared, right? So my short sides are going to be what? 1 and x. It's basically the square root of the first term. Square root of 1 is 1, and the square root of x squared is x. The radical, r, is going to equal the hypotenuse. So now let's go ahead and set up our graph, our little, not graph, but diagram, just like we did when we were composing it into a trig algebraic function from a trig expression. We have theta in quadrant 1, just something to reference, and we have a reference triangle drawn. So let's go ahead and label our two short sides, 1 and x. Does it matter which one? No. So let's go ahead and do it maybe the way that maybe makes more sense. Let's label the horizontal x and the vertical 1, because we're used to calling the horizontal x. If that's the case, what would the hypotenuse be? The actual radical. Now that you have all three sides, you got to work backwards, okay? So here's how we're going to do this. We want to end up with the radical over x. The radical over x. So remember, the way that we ended up with these specific ratios is this outside thing. So we're going to put the trig function first from our diagram that generates the radical over x. Well, the way I've labeled it, my radical is r, and my x is x. So what ratio is that? That's secant, right? That's the secant ratio. So we're going to work from the outside in because we're doing it backwards. So the last thing I'm going to do is take the secant ratio, which should give me the radical over x. Now what I need on the inside is an inverse trig function that will generate that ratio. And so what you want to do is generate the nicest ratio. You want to generate the nicest ratio. I didn't choose secant. Secant chose me. I chose where to put my x and 1. I chose to put the x on the horizontal and the 1 on the vertical. Once I chose that, now secant chooses me. Because what do we want to end up with, Tyler? We want to end up with the radical over x. So now in my diagram, the radical is the hypotenuse and the x is the horizontal. What's the only trig function that takes that ratio of hypotenuse over horizontal? Secant. It's the only one. So now it has to be secant. But now I have a choice. There are 6 trig ratios, right? 6 of them?
Yeah, so you could have put x as the y value.
Yeah, and we'll do that next. We'll do that next. And it'll be different, but it'll be equivalent. So of the 6 ratios, which one is the nicest? Tangent? Tangent would be 1 over x. That's not bad. 1 over x is not bad. Anything that doesn't involve the radical is going to be nicer because the radical's big and ugly and cumbersome. Cotangent's the nicest ratio. Why? Because what's the cotangent ratio? X over 1, also known as plain old x. Okay? So when you can get plain old x, you're going to try and achieve plain old x. That's actually what we started with up here. The nicest ratio is just plain old x. So plain old x, in this case, the way I've labeled it now, is horizontal over vertical, which y'all just said is the cotangent ratio. So, do I put cotangent or inverse cotangent of x? I have to put inverse cotangent of x. That makes x now a ratio, not an angle. And guess what? You are done. That's it. There is an answer. Of course, there are others. Let's look at another version. If I would have chosen in the beginning, my 2 short sides are 1 and x. That's irrefutable. And the radical then has to be 1 plus x squared. But Tyler, if I had chosen to put my x on the vertical and my 1 on the horizontal, that would be my prerogative, right? As Bobby Brown says. It's totally your prerogative. You can do what you want to do. No one can tell you what to do. It's all part of the song. Now, if I am decomposing it backwards, working from the outside in, again, I need to end up with the radical over x. The radical over x. If I diagram it this way, my radical is still r, but now my x is the vertical. Which trig function is that? Cosecant. So that'll be working from the outside in. The last thing I want to do is pull up the cosecant ratio. And again now I want to generate the easiest ratio, which is x over 1, because it's just x. So which trig ratio then generates x over 1? The tangent ratio, right? But I can't just put tangent in there, lest I think x is a angle, not a ratio. So I'll put inverse or arctangent. So there is the other solution. Either one of those could be a multiple choice answer. I will always choose the nicest ratio, always. Now let's see if there's a pattern between the two. One of them was secant of inverse cotangent, and the other equivalent one was cosecant of inverse tangent. It's one or the other, but is there a connection or a pattern betwixt the two? They're complementary. Very good. If you have a secant on the outside, the other option, at least in this case, is the cofunction of that secant, which is cosecant. And similarly on the inside, if you pull an inverse cotangent, then this one will be its cofunction, inverse tangent. Now, one set of data, does that make a unanimous general pattern? No. I need more data, but maybe that holds true. So let's try it on example B. What's the first thing we look for? The radicand. Okay. Because it contains pretty much the DNA of everything. So let's go ahead and draw our little picture. There's my theta. Now notice under the radical we have 2 terms again, but now we have a minus sign. If you have a minus sign, then guess what? What? You have the hypotenuse and one of the short sides. Because the only time you're going to get a minus, look at answer choice B. The only time you're going to get a minus is when you're finding one of the short sides. And the positive term is going to be the hypotenuse squared. And the term that follows the minus sign is going to be one of the short side squareds. And in this case, the radical itself is the other short side, not the hypotenuse. That's the only way you're going to get a minus sign. So if you ever have this, if you ever have the square root of a squared minus b squared, a is going to be your hypotenuse. B is going to be a short side. It doesn't matter which one. And what's the other short side? The whole thing. A squared minus b squared radical is the other short side. Say what? Oh, I don't know. That must be one of the shorts. That must be one of the other sides. We'll see. Let's go ahead and identify it. So this is going to be hypotenuse. Let's just call this r squared minus a squared. So if r squared is 1, what is the hypotenuse, the radius? What's the square root of 1? 1. And one of the short sides, I'll call it a. If a squared is 9x squared, what's the square root of 9x squared? 3x. That's why there's a 3x in the top. All right, so now let's go ahead and assign values to our little diagram. The hypotenuse has got to be a 1. Gotta be a 1. But the other short side, I'm free to call it whichever one I want. Let's go ahead and do the 3x on the horizontal, simply because we're used to having the x on the horizontal. That means the other short side then would be the entire radical. Now that I have generated my triangle, I work from the outside in. The last thing I want to do is pull off this ratio, which is 3x over radical. 3x over radical in my diagram is horizontal over vertical, which is which trig function? Cotangent. Good. So that's the last thing I want to do. What's the simplest ratio from this triangle? 3x over 1. 3x over 1. Can't just get x, because not a side is x, but 3x over 1 is just 3x. So that would be the simplest ratio. So which ratio is 3x over 1? That is the horizontal over the hypotenuse, which is cosine. So I'm going to put not cosine, but inverse or arc cosine of 3x over 1, which is just 3x. And there you go. Presto magic. No, I actually prefer arc, believe it or not. I don't know. I've been doing inverse today. I don't know, but I do prefer arc. All right, let's see if our pattern holds true. What would the other equivalent one be based upon our pattern from part A? And we'll verify it afterwards. Tangent instead of cotangent. What is the cosine of cosine? What is the cosine of sine? Of cosine? Cofunction of cosine is sine. Right. You either add a co or you take away a co. So cosine would just be sine. Right? So this would be inverse or arc sine of 3x. Now let's see if that works. The other diagram would have still 1 on the hypotenuse. That's a given. It's gotta be a 1. But I can put the vertical now as 3x and the horizontal as the radical. Well, now let's see. If I want to end up with the 3x over radical from this new diagram, that's the vertical over the horizontal. That is, in fact, the tangent ratio. And now to generate the nicest ratio of 3x, that's going to be vertical over hypotenuse, which is y over r, which would be the sine ratio. So it does, in fact, work. Yay. So not a big deal. If this is a multiple choice question and you set it up one particular way and that answer is not there, you can just take the cofunctions of both of them and you have your second equivalent nice answer. Sure. Yeah. I wouldn't put 2 right answers. I would only put one of those 2 right there. So if you happen to do it one way and it's not there, then you have to know to do it the other way. Right. Yeah. All right, letter C. We have 1/3 times the radical. That one looks funky. That one is not in the format that we would like, right? We want it to be in ratio format. We want something over something. So multiplying by 1/3 is tantamount to doing what? Dividing by 3. So let's go ahead and do that. That'll be the square root of 9 minus 16x squared all over 3. Now remember, the radicand and the radical itself contain everything, because the radical is one of the sides for sure, and then the 2 terms under the radical are 2 of the other sides, squared. All right? So in this case, because it's 9 minus 16x squared, let's go ahead and list over here R, A, and B. Where A and B are the two short sides, and R is the hypotenuse. What is R? 3. It's got to be 3, because it's number squared minus. So whenever you have something minus, the positive term is the hypotenuse squared. What would be the other short side that we get from under the radical? 4x, right? 4x. It's the square root of 16x squared. And the other side then would be the whole thing. The whole kit and caboodle. You get both the caboodle and the kit. All of it. How could we simplify that? Is that equal to 3 minus 4x? The reason we don't do that is because that's not equal, right? We had that conversation at the beginning of the year. It's super tempting, right? It's super tempting. But if we write that to the 1/2 power, remember we cannot distribute the exponent because those inside are not factors but terms. So we tried to break that urge earlier on in the year, but it hasn't arisen that often since the beginning of the year, but it's still not true. So as Einstein said, simplify as much as possible, but not more than that. Okay? If you oversimplify this case, it could be wrong. All right, let's go ahead and draw our little reference triangle in quadrant 1. The hypotenuse has to be 3. You tell me, what do you want to call 4x, the vertical or horizontal? Horizontal, okay, so there's 4x, and the other side is 9 minus 16x squared. And now we begin deconstructing it. So you work from the outside in. The last thing you want to do is generate this ratio, radical over 3. Radical over 3 in your diagram is y over r. Which trig function is that? Sine. So we're going to take the sine ratio at the very end. Now we want to generate the easiest ratio. Your easiest ratio is always going to be your power of x over your constant. So what would that be here? It'd be 4x over 3, right? 4x over 3. That would be x over r. Which trig function is x over r? Cosine. So we're going to put inverse or arc. I'll put the arc here this time. Arc cosine of what? 4x over 3. Yep. And for kicks and giggles now, what would be the equivalent one that has a 4x thirds as its ratio? Cosine of arc sine. Good. You just take the cofunctions of them. And just like that, we're done with the notes. Another section in the book. You've learned more now than you have before any time in your history prior to this. Right? As opposed to your history after this. You don't really call it history if it hasn't happened yet. The history of the future. What if you had to study the history of the future? That would be weird. Yes! I'm just thinking out loud. I don't know. Yeah, it would. Butterfly effect. Yes, Araceli. On the homework. Okay. Momentito. Any questions on the notes? All right. Let us go to the homework, also known as the worksheet. Good. It's less pejorative, right? Yes, ma'am. Which one? The question after? Does it have a number? 16. Oh, yeah. These are good. These are the ones where you go to the key and just copy what the key has and you turn it in without thinking, right? No. The last ones are usually the fun ones, the applications. The whole reason you study all the stuff before this is so that you could apply it out in the real world. This is where this stuff is actually used. When am I ever going to use this stuff? Well, here's where it's used, right? By the way, the best answer to that, when are you ever going to use this stuff? The answer is never if you don't learn it. Sizzle. Okay. Oh, well, let's read it together. Maybe I wrote it in a foreign language. Calculator permitted. That means the calculator is allowed. Feel free to use the calculator. The figures indicate that the higher the orbit of a satellite, the more of Earth the satellite can quote-unquote see. Okay, the reason that's in quotations, maybe that threw you off, is because satellites are inanimate objects. They technically don't see anything, but they have a lens that can encompass a viewing area by which the person on the other end viewing that can see. And because C is not a complete sentence, the period goes inside the quotation marks at the end of the sentence. Well, that's why it's in quotations. No, I mean, that's exactly what the quotations mean. See, wink, wink, right? Which there's a whole group of people that go out there and look at homemade signs, and it's called unnecessary apostrophes or quotations. Sorry, unnecessary quotations. So like you'll see a sign that says free meat, and you're like, oh, it's free meat. I wonder what it actually is if it's not meat. Wink, wink, right? So that's exactly what the quotations mean. Let theta, S and H be as in the figure, and assume that the Earth is a sphere of radius 3960 miles. Hey, y'all remember this? We imported that number from the previous problem. Remember the hang on to your homework problem? Yeah, okay. So the Earth is not a perfect sphere, so we can't have a single radius. But we're going to assume it's perfectly spherical and that the radius is 3960 miles. Radian mode, you're welcome. There's the hint. All right, so here is a satellite, and it's above the Earth. And it's going to see, quote, unquote, okay, as much of the Earth as is encompassed in these lines that kiss or glance off the side of the Earth. What do we call those lines? Tangent lines. Good. Those are tangent lines. Okay, they glance off the curve at a single point. So it kind of looks like a yarmulke, doesn't it? Yeah? The Earth is wearing a little shaded yarmulke. And you could see in three-dimensional space then along this curve any piece on top of that yarmulke. Okay? I'm not saying the Earth is Jewish, but there you go. Now, we can measure the height of the satellite above the surface of the Earth by some amount, okay? If the satellite then goes higher above the surface of the Earth, it extends these tangent lines out further, does it not? And therefore, the yarmulke gets bigger. And now we can, quote unquote, see more of the Earth. Now, there is a limit to how much it can see, right? What, horizon? There is a limit. Very good. As the satellite approaches infinitely far away from the Earth, there is going to be a limit. It's never going to be able to, quote unquote, see more than a perfect hemisphere, right? Okay? Because it can't turn the corner. All right, good. So here's the diagram. We are calling the distance above the surface of the Earth h in miles. And we're calling the entire arc, this is two-dimensional now, we're taking the three-dimensional shape and making it a two-dimensional. We're calling the entire arc along the curved path that the Earth sees, we're calling it S for the German verb Strecke, which means distance, which we denote as the what? Arc length. Good. So remember, the arc length formula is r theta. And of course, what is the radius of the Earth? 3960. So that's a constant. So h is a variable and 3960 is a constant. Part A, express theta as a function of h. Express theta as a function of h. Okay, is that going to be hard? No, not if you think about it. What do y'all remember from geometry about tangent lines and the radial lines? How are they related? A tangent line to a circle and the radial line. They're perpendicular. They're 90 degrees to each other. So this makes not one, but two right triangles. Yeah? So if I'm trying to write theta as a function of h, well, here's theta. H is involved with the hypotenuse, right? And I guess I'll use that short side instead of the other short side, which goes off into space. What is this other short side? Do I know what that is? That's also called the radius of the Earth again. All right? So, if I have theta as my central angle, I have the hypotenuse and the adjacent. Which trig function is that? SOHCAHTOA. Or it's X and R. Cosine, thank you. Cosine. That's the cosine. Cosine. So cosine of theta is the adjacent, which is 3960, the constant, all over the hypotenuse, which is what? 3960 plus h. H is just the distance above the surface of the Earth, so it's over 3960 plus h. Now, it says to write theta as a function of h. Right now, we don't quite have that. We have cosine of theta as a function of h. So, we need to solve for theta. How do we solve for theta? Arc cosine both sides. So, theta as a function of h, instead of f of x, we're putting theta of h, is arc cosine of 3960 over 3960 plus h, the distance above the surface of the Earth. Okay? So good so far? So good so far. Letter B, express the distance s, which is the arc length, as a function of theta. Okay, doke. Now here you want to be a little bit careful, because s we're calling the entire arc that's shaded in pink, where theta is just the angle of one of those right triangles. So if s equals r theta, then what is my theta for the entire arc? Not theta, but what? 2 theta. I have a theta on each side, and they're the same theta because the 2 right triangles are congruent. Yeah? All right. So the arc length now is the radius. What's my radius? 3960 times what? My central angle, which is not theta, but in this case, rather, 2 theta. So if I simplify that, 3960 times 2 is 7920. You agree? Okay. Theta. So does that answer the question? S is a function of theta? I believe so. So S of theta is 7920 times theta. Yay! We're answering questions. Now it says, part C, express the distance S as a function of H. How are we going to do that? Well, I gave you a clue. I hate giving you clues. It kind of spoils the fun. Use your results from part A and B. All right, so in part A, we have theta as a function of H, and in part B, we have S as a function of theta. We're trying to find S as a function of H. How are we going to do that? A little something called the transitive property. Well, if we know that theta, if S is 7920 times theta, right? What if I leave parentheses where I have a theta? Is there any way that I can replace theta with something that's equivalent, but in terms of H? A. So it's going to be arc cosine of 3960 all over 3960 plus H. So there you go. This is a great question because I'm basically walking you through it and telling you to find componently, individually, all the things that you need to answer the final question. Now, why is this function or this formula useful? This allows you to get at least the 2-dimensional arc that the satellite can quote-unquote see simply as a function of how high above the planet Earth it is. It takes it all into account. So now it's a plug-and-chug formula. If you know how high the satellite is above Earth, plug it in here, and you can determine quite easily then how much the satellite can see in 2 dimensions. It gets a little bit more interesting if you have 3 dimensions. You'll have to use surface area or calculus. All right, so then I'm not going to do part D and E for you, but I want you to do it because I'm just giving you 2 inputs. And one of them I'm giving you the height and asking you for S. And the other one I'm giving you S and I'm asking you to solve for H. So then it's just algebra. Once you have the formula, it's just a plug and chug. That's mainly what your physics class is, right? They hand you the formulas. You just have to plug and chug. Here, we're inventing our own formulas, which is a lot more fun, right? We're going green math. We're not using prepackaged formulas. We're growing our own formulas. Growing, quote unquote. All right. All right, any other questions? Yes. Sure, I won't steal your thunder from the worksheet, but let's go ahead and invent one. How about the square root of 5 minus 4x to the 8th power, bless you, all over 2x to the 4th. I just made that one up. Let's make it plus. 5 plus 4x to the 8th over 2x to the 4th. We want to decompose that into 2 trig, inverse trig compositions, okay? First things first, look at your Radican. It contains all the DNA that you'll need to decompose it. You notice the 2 terms are both positive, right? If they're both positive, then we're staring at the 2 short sides squared. All right, so if you want then, list A, B, and R. If it helps you to list them first, that's great. So what would A be? The square root of 5. Yeah, it doesn't have to be a perfect square. What would B be? 2x to the 4th. Good. It's the square root of 4x to the 8th. And what would R be? The whole thing. Good. Excellent. And now that you have those listed, you can label the sides. The only thing now that is locked in is the hypotenuse. It's got to be 5 plus 4x to the 8th. What do y'all want to call the horizontal? Square root of 5? Good. I'm glad we're kind of doing a little bit different. And well then, by default, there's only one place left for the other one to go. Now we begin the decomposition working from the outside in. We want to generate at the end the radical over 2x to the 4th. The radical over 2x to the 4th in your diagram is hypotenuse over vertical, r over y. Which trig function is that? Cosecant. So the last thing we need to do is pull up the cosecant ratio. The next thing we want to do is generate the ratio by the simplest ratio possible, which is always going to be your power of x over the constant. So that's going to be, for us, 2x to the 4th over the square root of 5. Which ratio is that? Tangent. So we'll put arc or inverse tangent of 2x to the 4th over the square root of 5. Close, close. What? No, heck no. Again, the only reason we rationalized was so that the 2's and the denominators on the unit circle were the same. In general, there's nothing wrong, absolutely nothing wrong with having a radical in the denominator. You can rationalize the numerator just out of preference as easy as you can in the denominator. So rationalizing has to serve a purpose. And the reason, again, we did it on the unit circle is because some of our ratios were 1/2 and some of our ratios were 1 over the square root of 2. So it's just convenient then on the unit circle to rationalize the denominator so that we would have our denominators all the way through of what? 2's. And that was convenient because then when we took the tangent and cotangent ratios, the 2's would just divide out. That was the purpose of rationalizing the denominators when we did that. In calculus next year, we're going to learn a method called rationalization conjugation for evaluating limits. And we'll be rationalizing the numerator almost as often as we're rationalizing the denominator. It's just an algebraic technique that gets rid of the radical from where it currently is. So, I don't know, at some point in your career you were told that it's just taboo to have a radical in the denominator. That is not true. That is not true. There's a reason for that algebraic process, okay? And it's just a stylistic or some other preference. But there's nothing wrong with the radical in the denominator. Okay, what would the other answer be? That was a little mathematical aside. Secant and arc cotangent or inverse cotangent. Yeah. So I will always choose the simplest ratio. Remember, there are 6 ratios you can pull off, but the simplest ratio is always the power of x over the constant. The power of x over the constant. So that's what you should shoot for. Okay? All right. I think we'll stop the recording now and maybe answer other questions. Quiz tomorrow. It'll be anything from this set of notes or worksheet, including maybe a satellite problem, maybe. And you'll have the rest of the time after that to conclude your worksheet, which